Science in pajamas. Science in pajamas. All right, so today we are doing another field trip to my kitchen, and this time we're going to talk about the properties of water. Water is super important because without water, life cannot exist on this planet. Every living thing needs water. Every cell, whether it's a multicellular organism or a single-celled organism, every individual cell needs water to survive. Without water, it would dehydrate, it would die. So yeah, water is very essential to life, hence why we're talking about it, even though I am a biology teacher. But let's not nitpick here or there. We're still going to talk about some of the properties of water. Now, you might remember that the chemical formula for water is H2O. What that means is 2 hydrogen, 1 oxygen atom are connected in order to form water. So it's a very simple molecule. Now I do want to review some of the different things we talked about in previous videos involving bonding. So here we have 4 water molecules. So we have 2 H's and an O. So 2 hydrogens, oxygen, 2 hydrogens, oxygen, 2 hydrogens, oxygen, 2 hydrogens, oxygen. Now the oxygen and the hydrogen are covalently bonded together. So within this molecule, this one water molecule, the oxygen is covalently bonded to the 2 hydrogen, meaning that they are sharing electrons in order to have a stable outer orbital. And that's the same with all 4 of them. Now you might have also hopefully slightly recognized these other symbols I drew from one of our previous videos. In between the water molecules is what we call van der Waals forces. Now this is a type of intermolecular force of attraction. Sorry, I got a few mosquito bites on my knee. So what this means is that they form a weak attraction to each other, not quite a full bond, but similar to it, and that allows them to stick together. Now, the reason why they're able to form this intermolecular attraction is because water is a polar molecule. Now, polar meaning that there's something different about the 2 ends of it, and that has to do with charge and electrons. When the water molecule, when the oxygen and the hydrogens bond together, it kind of forces all of the electrons closer to the oxygen, giving the oxygen a slightly more negative charge. Now, we're not saying that it's an ion and it's lost electrons. We're just saying that the electrons are kind of pushed closer to it. So because of the abundance of electrons, and we know electrons have a negative charge, it has a slight negative charge on that end. Now, because the electron is being shared between the hydrogen and the oxygen, that means that here and here, the closest thing to the outside of the hydrogen atom would be its nucleus, so where the protons are, and protons are positive. So that gives the 2 hydrogen atoms a slightly positive charge. Now, overall, it is still neutral. The slightly negative oxygen balances out with the slightly positive hydrogens. So overall, it is neutral, but on a molecular scale, you can think of it like a magnet, where on one side you have one attractive force, and the other side you have the opposite attractive force. Now, if you want to see that diagrammed out, check out my video on the chemical bonding. We actually draw out what it means to be polar and how we go into more detail on van der Waals forces. We're just doing a quick recap here because it is responsible for a lot of the cool properties that water shows. So, because the hydrogen is slightly more positive and the oxygen is slightly more negative, this allows a weak attraction to form between the hydrogen of one water molecule and the oxygen of another. Now we call this a hydrogen bond because it involves, well, look at that, a hydrogen atom. Now again, it's a weak attraction. It is easily broken, but it also allows water to stick together and to do some pretty cool things. So it's all because of the polarity causing the van der Waals forces, which means that there are hydrogen bonds between the water molecules. Notice again, they're between different water molecules. We're going to talk about what that means in terms of the properties. So, what you can see is I have stuff spread out all around me to help us demonstrate that. I am going to start with this piece of chromatography paper. What I'm going to do is I'm going to draw a dot on it. Now, what I'm going to do with that dot, and I'm actually going to leave this right here so you can kind of see that. That'll be better. You can kind of see that I don't mess with it once I put it in. And just kind of see the top of the water. I'm going to put this down into it so that only the very, very bottom of the paper is touching the water. Now, I know you can kind of see it on the screen. So here's the top of the water. You can see that the dot is above the top, but the bottom of the paper is touching the water. So we'll make sure it's nice and submerged. All right, I'm going to take this down, and we're actually going to come back to this in a little bit. We're going to come back to this in a little bit. I'm going to leave that right there so you can kind of keep an eye on it. There you go. So we'll come back to that. Well, some of the things that polarity allows water to do is stick to things. Oh, my kids for the past 2 years have been driving me nuts with the question, is water wet? The answer is no. It makes things wet, but it itself is not wet. It's actually sticky. Yeah, because of this polarity and the bonds, it's actually a sticky substance. We don't think about that because when we think about sticky, we think of, like glue, honey, etc. But it's actually not that different. So I'm going to put this here, and it's mostly because I want you to be able to see there's just a little circle cork board. That's all. All right, so what I'm going to do is I'm going to take some water in my hand. I'm going to drop it on. Let's see if I can get a little closer to the edge. So you might start to notice it's kind of bubbling up. Not like bubble as in foaming, but bubbling as in, it looks like there's a bubble of water, like a sphere of water on top of it. Now I don't want to move this because I could knock it and cause it to kind of shift a little bit. But I'm going to try and get this as close as possible. You can kind of see it right there. So right there. How it kind of bubbles up a little bit. It forms that actual 3D structure. It's not like it's necessarily spread along it. It is bubbled above it. And you can kind of see it again. There you go. So now you can see how it's above the actual cork. It is sitting above it. It's forming like this arc of water. We have also seen things like this in terms of dew or, when there's droplets on the windshield. It's because the water is stuck together. We call this cohesion. So cohesion is what we call it when, get this a little closer so you can see it again. The water molecules have formed those hydrogen bonds and they don't want to separate. It is a weak force of attraction, but still a force of attraction. So the water molecules are stuck together, which is what allows them to, instead of just sliding along and spreading out on the corkboard, what allows it to bubble up instead and form this 3D structure. So it's because of the cohesion, the ability of the individual water molecules to form a structure and to actually stick together to keep that structure intact. But I can break those bonds fairly easily. All I gotta do is wag my finger through it and I can spread it out. So what that means is, again, they're weak forms of attraction. It allows them to form that bubble, essentially, up until a certain point. After a certain point, when even the force of gravity is too much, it'll break those hydrogen bonds and cause the water to spill over. You can also see this if you're trying to top off a glass, like a glass of water, and how it'll form, like, if you're very, very careful, it'll actually form a layer of water above the rim of the glass. But at some point, you put too much in there, gravity can overwhelm the hydrogen bonds and it spills down. All right, so that's cohesion. I'm also going to talk about something called adhesion. So adhesion is when water molecules stick to other substances. So cohesion is when water molecules, because of their polarity, form hydrogen bonds with other water molecules. Adhesion is when water molecules form hydrogen bonds because of polarity, but with other molecules. So like, I just put my hand in there. I can, kind of shake it off and all that. But in the grand scheme of things, violently shake the wetness all over. You see my hand is still wet. So my hand is wet, not the water, so please stop asking me that question. The water is stuck to me. It's adhesion. It has formed hydrogen bonds between the water molecules and the skin of my hand. Now again, it's weak. I can break it. You take a towel, rub it. I break those hydrogen bonds very easily. And when I'm done, no more shininess to indicate wetness. The water's gone. I broke the hydrogen bonds between myself and the water molecules. Gosh darn, these mosquito bites are driving me nuts. Now that's also why after you have taken a shower or a bath or gone swimming, why your hair stays wet long after your skin dries up. Because you towel dry your skin, you're all good. But even if you towel dry your hair, it usually stays damp. And that's because the water isn't just bonded to one or to the outside of the hair molecule, it's bonded all around it. So it's actually hydrogen bonded to your hair. So let's say this is a hair molecule, or not hair molecule, a hair strand. That's a hair strand. That's a hair strand. So we have 3 hair strands right there. So what happens is the water is going to hydrogen bond, not just to one side of the hair, it's going to bond all the way around it. So it's 360 degrees of bonding, of adhesion to your hair molecules. So 360 degrees of adhesion. So unless you plan on taking each individual strand and drying it with a towel, it's going to stay damp. But it's not just that. We also see this in conjunction with cohesion. Because what happens then is the water molecules on this strand of hair and on this strand of hair will form hydrogen bonds with each other. So the water molecules form hydrogen bonds with each other, which is cohesion, and they're stuck to the hairs, which are adhesion. And that's why a lot of times after your hair gets wet, why it could clump. So like if my hair gets wet, it clumps a lot, meaning it forms like, instead of just individual strands, like it's all frizzy, you can see individual pieces now. But when it gets wet, it tends to group up almost. Let's see. I'll take my glasses off because I'm a little OCD about getting stuff on my glasses. So you can easily see how there's a whole bunch of different individual strands. But then I put it in the water, and you can see how it's actually getting closer together, how it's more clumped than it was. Let's make sure all the hair gets submerged this time. And it's all clumped together now. Because what's going on is, yes, I know, frizzy hair. I need a haircut. So what's going on is the water is stuck to the hair. So it's formed hydrogen bonds between the water molecules and my hair. And that's adhesion. And then the water molecules on one hair strand is going to form hydrogen bonds with the water molecules on another hair strand. So that's cohesion. And even if I take a towel and try and dry it off, you can see it still has some of the qualities of being wet. It still kind of clumps together because it still has some of the hydrogen bonds. It's not as frizzy and separated as the rest of my hair. So that's just some examples. So that's cohesion, adhesion we talked about, hydrogen bonding we talked about. All right. Let's talk about another way that water is unique. So typically, when you freeze something, when you lower the temperature and it goes from a liquid state to a solid state, a lot of times what happens is when you take away the heat is just a form of energy. When you take away the heat, the molecules slow down and they'll actually condense into a denser material. So a lot of times, like let's say gold or any kind of metal, when you heat it up and it's in a liquid state, it is less dense than when it cools back down and goes into a solid state. What happens in the metals is in the liquid state, it's more flowy. The molecules kind of can separate a bit more because of the extra energy from the heat. But then when you take that extra energy away, when it cools back down, the molecules slow down and they will solidify closer together. Water is unique in that it doesn't actually do that. What happens is it's actually denser as a liquid than it is as a solid. Here I have some ice cubes. Now, they've been sitting out for a few minutes, so they've kind of started to melt, but this will still work. And I got my bowl of water. Now, what happens when I put ice cubes into the water? Well, if they were more dense, they should sink, right? Hitting the bottom first and then bouncing back up doesn't count. So as you can see, they are floating, which means they are not more dense like we would expect. If they were more dense than the liquid water, they would sink all the way down to the ground or to the bottom of the bowl. But they don't. They float, which means that the water is more dense and the ice is less dense. Now again, we wouldn't normally expect to see that, but we do. So what that means is, as a liquid, the molecules of the water stay closer together, probably due again to the polarity and the hydrogen bonding. That's my hypothesis. I don't know for sure. I'm not a chemist. I'm a biologist. But when they cool down and go to their solid state, they actually spread out a bit more to make more of a crystalline structure, and that's how we get the ice. Because the molecules spread out, they now are less dense than when the molecules are closer together in water. So we have less dense ice floating on top of the more dense liquid water. Now, both of these are the same substances. We can agree on that. They're both water. It's just a matter of water in a liquid state and water in a solid state. But both of those have the exact same chemical composition. They're H2O. That's their chemical formula. This ice cube is made out of H2O molecules. They've just had a lot of energy taken away from them, which is why they have solidified into this solid structure. But as you can see, all of my ice cubes are melting. And they are just blending right on in with the rest of the water molecules. I'm not adding something new to this. It's just solid H2O melting into liquid H2O. And then if I was to put this on the stove and boil it, and you just see like all the bubbles and the steam coming off, what I'm doing is warming it up to the point where then our molecules within the liquid get even further apart and it turns into a gas. What all that steam is what we call water vapor. It is a gaseous version of water. All right, so there's that. Hope you've been keeping an eye on this guy. Look at that. You've been going crazy over there. All right. So we talked about how it's less dense as a solid. We talked about cohesion and adhesion, talked about hydrogen bonding. It's also the hydrogen bonding that makes water, as we like to call it, the universal solvent. We call it the universal solvent because given enough time, it'll dissolve just about anything. And I'm not even kidding about that. I'm going to try and lift this glass up a little bit so you can see it a bit more. So here I have just a glass of water, and here I have some sugar. And when we talk about dissolving substances, we're not chemically bonding them. We're just simply mixing them into the same container, but we're spreading it out. Now, this would take less time if the water was warm, and that's simply because, like we were saying with the ice cubes, when you apply heat, heat is energy, and energy causes molecules to move faster. Well, I don't want to spend the time boiling water right in front of you, so I'm just going to take a few extra moments to stir this a little vigorously. All right. So you might have noticed when I first put the sugar in the water that it kind of went cloudy for a moment. But now you can't even tell. It's still clear like the water was before. Now when I put these in, this is actually an example of a physical reaction or a physical change. I did not change the water into something new. I did not change the sugar into something new. They are not bonded at all. All they're doing is hanging out together in the same glass, but they're spread out. So the sugar molecules have spread out from the clump of sugar molecules, and now there's sugar molecules mixed in with all the water. Now the reason why this occurs, why water does this and keeps it separated out, is again because of the polarity. Remember how we said that the slight negative charge on the oxygen and the slight positive charge on the hydrogen can form bonds between things? Like it form bonds with other water molecules, hydrogen bonding, which is why cohesion occurs. And it can also form those same hydrogen bondings because of the polarity with my skin, thus adhesion. Well, that's kind of what's going on. The polarity on the water molecule actually formed hydrogen bonds with the polarity of the sugar molecules. And that's what allows the water to pull the sugar away from the clump and dissolve it into the mixture. Now I can actually evaporate this water, which means I can boil it, heat it up, have it go bye-bye in a gaseous form, and the sugar would still be left at the bottom of the glass because the sugar is not bonded like permanently. It's not ionic, it's not covalent bond. It's just that weak hydrogen bonded nature. Now that doesn't mean that you actually fully bond the two molecules and make something new out of it. It's just more like magnets. You can easily separate them. So hopefully that helped with this. All right. I have one more thing to talk about before we get back to this guy. And that is, again, relating to adhesion, how to read a graduated cylinder. Now this one's a little wider, and I know it's hard to see because it's kind of this not quite opaque, cloudy color. But what you might notice sometimes when you look at a graduated cylinder is that the water at the very, very top of it, sorry about that, sometimes looks a little bit curved. Now again, I know it's kind of hard to see in this, so I also drew a diagram as well. Oops. So a lot of times you'll see this curve, how it's higher on the edges and lower in the middle. And the reason for that is, again, because of adhesion. What happens is the water is actually hydrogen bonded to the edges of the graduated cylinder, which is why it stays a little bit higher. Whenever you want to measure a graduated cylinder, you always measure at this bottom part. We call this curve the meniscus. And you always want to measure at this bottom part here, because that's the part that's going to show the more accurate amount of water, as opposed to this, how it's higher on the ends. That's just because some of the water is hydrogen bonded to the sides of the cylinder. So it's just kind of stuck there. Not that it's actually, higher on the sides. It's just that it's stuck to the edges. All right. And last but not least, let's come back to this guy. I'm pretty sure you can see something has definitely changed here. So what we call this is capillary action. Remember, we put the bottom of the paper into the water. The water was only at the bottom. You can still see that it is submerged at the bottom there. Now what happened is the water absorbed into the paper. And when it absorbed into the paper, that's adhesion. But then the water is still hydrogen bonded to other water molecules, so it pulls more water in. And as it pulls more water with it, it pushes the first water molecules higher. Well, the new water molecules that were just pulled in are also hydrogen bonded to other water molecules that are still down here in the cup. So it pulls them in, pushing everything higher. Pulls more in, pushes everything higher. And what we get is the water is all the way up here now. So now we talked about the setup and what happened. I'm going to take this out so we can look at it a little bit closer together. Keep that from dripping. And that's actually why we put the spot on the paper with the marker. Because yeah, you can kind of see that the paper is wet, but it gives you a very striking visual of what's going on. So as the paper went up and it finally hit the spot, it actually started dragging the different components of the ink with it. So it was pulling the ink with it. So again, got some adhesion going on. And as it pulled it, you notice that it changes color. It's not so much that the ink itself is changing color, but the different components are of different sizes. And the larger, heavier components can't be dragged up as high. Because remember what we said before, eventually gravity wins out and it stops it or pulls it back down. So it can only go so high with adhesion until gravity will not let the water drag the heavier components up. But the water can still drag the lighter, the smaller components higher and higher, which is why you see this transition from black to blue, because a lot of the darker dyes are bigger and heavier, they have more mass, so they can't be pulled up as high. But then the blue is a smaller molecule, and it can be pulled up even higher. Now this is just where the water stopped. If we let it keep going, it'll pull pretty much as far as it can. But yeah, all right, so I hope that helped you to understand the different properties of water and hopefully helped you to learn a bit more about why water is so cool. But in the meantime, you guys, stay awesome, stay amazing, and most importantly, stay safe and healthy. All right, you guys, until next time, you take care of yourselves. Bye-bye.